Hi, welcome back. So in this video, we're going to go through some examples of solving integrals with integration by parts, and I'll start the video by giving you the method that we use to actually implement the integration by parts formula. So here is the integration by parts formula. It has the integral of u dv, and this is what we don't know how to integrate. So this is the problem that we're given and we're not sure what to do with, so we're going to try integration by parts. We can then rewrite it as u times v minus a new integral, and that new integral is v du. And the hope is that that new integral is something we do know how to integrate. So in order to use integration by parts, we have a couple of steps we need to follow. So for the method, the first step is that we need to choose the u and the dv. So we're given an integral and we're trying to imagine it in the form u dv so that we can rewrite it using the right-hand side of this formula. So we need to pick which part of the integral we're given is u and which part is dv. And then in order to use the formula, we're going to need to find du and v. So remember, du is the derivative of u, and then v is going to be the antiderivative of dv, whatever you pick for dv. Then, once you have all of these parts, you just need to assemble the formula for integration by parts and evaluate it. So you're going to put everything back together as uv minus the integral of v du, and then hopefully solve that new integral you've created on the right-hand side. Okay, let's try this method on an example that we saw in the previous video. We're going to do the integral of x times cosine of x dx. So to do this integral, our first step is that we need to choose what we want to be u and what we want to be dv. So here, I'm going to actually choose incorrectly the first time, just to show you what happens when you do it wrong, and then we'll do it right the second time through. I'll have a separate video where I go through some overall suggestions for how to know what's u and what's dv, but for now we're just going to practice choosing some things and seeing what happens. So my options here are basically that x is u, or cosine x is u. So again, I'm going to choose incorrectly the first time, and if you're doing this for the first time, you probably have no idea which one to choose. So we're just going to pick one, I'll pick the wrong one, and I'll show you how it doesn't work. So we're going to choose u as cosine of x, and dv to be x dx. So we're replacing everything in the integral with either u or dv. And this is our first step. So I like to organize mine in this way, where I write the u up in the top left and the dv in the bottom right, because now we're going to take the derivative of u, and I'm going to write that below my u, and we're going to find the antiderivative of dv, which I'll write above. So first, the derivative of cosine is negative sine dx, and now we have to find the antiderivative of our dv. So this is the antiderivative of x dx, which is 1/2 x squared. I mentioned this in the previous video, but when we're doing integration by parts, I'm not going to worry about finding my plus c or putting it anywhere until the very end of the problem when I tack it on in order to say that it could represent any constant. So in the meantime, throughout this process, we're not going to worry about plus c's, we'll just do it at the very end. Now that we have all of our components, we're going to assemble them into the integration by parts formula. So we do the integral of u dv, that's our x cosine x. We're going to rewrite it as u times v minus the integral of v du. Remember, I've done this wrong intentionally, so you're going to see that it doesn't really look very good when we start to write things out. Okay, so I have u times v, that's cosine of x times 1/2 x squared, and then I'm subtracting the integral, which is v, 1/2 x squared, times du, which is negative sine x dx. And so I'm left here with this new integral that doesn't really look any easier to solve if you ask me. I still have something with x's times a trig function, and I don't know how to integrate that. That was my problem to begin with, was that I had x times cosine of x. So here we've chosen incorrectly, as I did on purpose to show you, and we've ended up with this integral that isn't any easier to solve. So this should be a good indicator to you, if you're working through these problems, that you chose incorrectly and you need to swap your u and your dv, or think of something different. So let's try again, this time using the correct substitution, which is going to be that u is equal to x and dv is equal to cosine x dx. Okay, so we're letting u be equal to x and dv be equal to cosine x dx. Then we need to find the derivative of u and the antiderivative of dv. So we need du and v. So the derivative of u is just the derivative of x, which is 1, and then we write dx. So we have du is dx. Then the antiderivative of dv, we're finding the antiderivative of cosine x dx, which is sine of x. Okay, so now that we've chosen u and dv, we just need to assemble again, and hopefully we should have an integral that's easier to solve when we do this. So we do u times v, that's x times sine x, and we subtract the integral of v du. So v is sine, and du is just dx. So seeing this, I'm feeling much better, because I know how to find the antiderivative of sine. That's something I can do, and I'm feeling confident that I can now finish this problem and solve it. So to complete the problem, we just need to compute this new antiderivative and write our final answer simplified. So the antiderivative of sine is negative cosine. So I have x sine of x minus negative cosine. Then the minus minus becomes a plus. So I have x sine of x plus cosine of x. And then I'll add on my plus c here to help me represent a general antiderivative. So after all of this, we can conclude that the antiderivative of x times cosine of x is equal to x times sine of x plus cosine x plus c. Just remember, at any point when you get your final answer, if you want to check by taking the derivative, you can go ahead and do that. So you could take the derivative of x times sine x plus cosine x plus c and make sure you're getting x times cosine x. Just remember, when you do this, you're going to need to use the product rule on the x times sine of x in order for it to work properly. But at this point, we have finished the problem and we have found our antiderivative. Okay, let's do another example. This time I want us to evaluate the integral x times e to the 3x dx. So here, remember, our first step is that we need to choose u and dv. So my options are either that u is equal to x or u is equal to e to the 3x. So last time we used u is equal to x, so I'm going to use that same substitution again here, and it is going to work for us. I'm just going to go ahead and show you the correct u substitution because I know what it is. And again, remember, in another video, I'll show you some tips for how to know how to choose. But honestly, choosing the wrong one isn't that bad. You can try it and then you'll mess up and be like, okay, I picked them wrong, and then you'll switch them, and it's not that big of a deal. Happens to me all the time when I'm doing a complicated integral. So now that we have u and dv, we need to find the missing components, which are du and v. So the derivative of u is just dx, and to find v, we're going to need the antiderivative of e to the 3x. So to technically write out all of the steps for finding the antiderivative of e to the 3x, we would probably use a u substitution where we let u be 3x, and that u would be different from the u we already picked for integration by parts. But since this is a pretty straightforward u substitution, I'm just going to write down the antiderivative, and you can check it for yourself, or you can do a whole separate step where you do u substitution if that's still helpful for you. But I know that the antiderivative of e to the 3x is 1/3 e to the 3x. That 1/3 is there to counteract what happens when we multiply by the derivative of the exponent, which would be 3. So now that we have all of our components, we're going to just assemble them into the integration by parts formula, and hopefully we'll have a new integral to solve that's a little easier for us to do. So I'm seeing that I have u times v, so that's x times 1/3 e to the 3x, and then I subtract the integral of v du, where v is 1/3 e to the 3x, and du is just dx. So looking at my new integral, I'm feeling confident that I can solve this because it's really just 1/3 times the antiderivative of e to the 3x. and I actually already integrated e to the 3x since it was my dv I chose above. So simplifying this a little bit, I have 1/3 x e to the 3x minus 1/3 times my antiderivative. My antiderivative is 1/3 e to the 3x, and so putting everything together, I have 1/3 x e to the 3x minus 1/9 e to the 3x, and I'll put here my plus c to represent a general antiderivative. So in conclusion, I can write that the antiderivative of x e to the 3x, or the integral of x e to the 3x dx, is equal to 1/3 x e to the 3x minus 1/9 e to the 3x plus c, and I've completed my problem. Again, you can find the derivative of what we just found as our solution to make sure it matches what we were trying to integrate, but that's up to you, and that's an additional extra step to confirm your final work if you'd like. Okay, so these are two examples of using integration by parts to solve antiderivative problems. I have another video where we find the antiderivative of natural log using integration by parts, and another video with some tips and tricks for how to determine which u and dv to pick when you're given one of these problems. Thanks so much for watching, and I will talk to you in the next one.